Welcome to Module 6 of the course Ultrafast Optics and Spectroscopy. In this module, we will learn how to construct ultrafast laser. We'll begin with Lambert-Beer's law, which connects the absorption of light to the properties of materials through which light is traveling. According to this law, absorption is observed as a decrease of the number of photons in the beam while transmitting in the medium. In linear optical regime, the decrease of intensity in z direction is proportional to the intensity. This is the Beer-Lambert's law, and here A is proportionality constant, which is also called absorption coefficient. After integrating this equation, we get an exponential function, which suggests that intensity of the beam, incident beam, will decrease as a function of L. If A is positive, and that is called absorption. The idea of laser comes when A for the medium becomes negative. In that case, what will happen? Light amplifies its intensity as it propagates through the medium, and that is nothing but laser. The name laser originates from an acronym of light amplification by stimulated emission of radiation. As the name suggests, amplification of light is achieved based on the stimulated emission process. What is stimulated emission? In 1917, Einstein identified three independent processes which contribute to the electronic transition between two states: absorption, spontaneous emission, and stimulated emission. Each process is associated with an Einstein coefficient, which is a measure of the probability of the respective transition. Absorption is a process by which a molecule or an atom is excited from lower state 1 to higher state 2 by absorbing a photon with an energy E2 minus E1 induced by incident electromagnetic radiation. So, spontaneous emission is the process by which an electronically excited molecule or atom spontaneously decays from upper state to the lower state. So, spontaneous emission is not induced by any external electromagnetic field. On the contrary, stimulated emission is the process by which an electronically excited molecule or atom jumps from upper state 2 to lower state 1 induced by incident electromagnetic radiation. Thus, technically, absorption destroys an incident photon, while stimulated emission provides or produces an additional photon. Furthermore, in stimulated emission, emitted electromagnetic wave and incident wave, these two waves, stay in phase. This is indicative of staying in phase. This is why stimulated emission is coherent, forming a unified whole, and spontaneous emission is incoherent. Emission occurs in all direction and with random phase. Consequently, the incident radiation is amplified in stimulated emission. So, we need stimulated emission always for the amplification, or negative A in Beer-Lambert's law. This is the physical basis of light amplification in lasers. More specifically, this is the idea behind negative absorption coefficient in the Beer-Lambert's law. Quite unfortunately, condition to achieve stimulated emission is not thermodynamically favored. Consider a light beam with incident intensity I naught propagating along a laser medium. Consider two energy levels, 1 and 2, populated. N1 is the population for the first state, N2 is the population of the second state. Now, the rate of absorption, this is absorption process, and this is stimulated emission process. So, we can write down that rate of absorption is going to be product of intensity, probability of that transition, and population. Similarly, rate of stimulated emission will depend on intensity, probability. This B is Einstein coefficient, which represents the probability of that respective transition, and the population. Here we note that it is the same probability which is acting for absorption as well as stimulated emission. They are the same process, but their starting energy state and ending energy states are different. To amplify light intensity now, which is called act of lasing, the rate of stimulated emission has to overcome the rate of absorption. Gain or loss of intensity thus depends on the magnitude of N1 and N2, because we have to find out what is the relationship we have between IBN1 and IBN2, and depending on, which means that depending on N1 and N2 magnitudes, we will be able to find out which rate is dominating. Normally, under normal thermodynamic equilibrium in which Boltzmann population distribution is obeyed, N1 is always going to be N2. N1 is always going to be greater than N2, and therefore, there will be a loss, mostly absorption in the medium. So, loss dominates, which means that incident beam intensity will decrease as it propagates through the medium. However, if N2 greater than N1, this condition is achieved. In order to have this condition achieved, stimulated emission must exceed the loss. And this is a condition which is called population inversion, inverted population. Normal population distribution is always going to be higher population in the ground state than upper excited state. But in order to achieve act of lasing, I need to have inverted population, and this is called population inversion. which features a negative temperature in Boltzmann distribution. As long as there are more atoms or molecules in the upper level than in the lower level, stimulated emission can dominate. The first emitted photon will stimulate the emission of another photon, then two photons subsequently stimulate the emission of more photons, and so on. Thus, cascade of photons grows, resulting in the amplification of emitted light. Spontaneous emission also emits photons, but they are incoherent, emitting in all directions with random phase. Now, there is an important question here. How do we achieve population inversion? In order to achieve population inversion, we need more than two energy levels. We cannot deal with only two energy levels. We need system which will exhibits many energy levels. Let's take an example of 4-level system which is shown here in these slides. In this case, pump beam transfers the population from 0 to 3. This is a pump beam I am using, is transferring population from 0 to 3 with the help of pump. Now, this 3 population is rapidly decaying to 2, level 2, and this level 2 is long lived excited state. Stimulated emission then occurs from level 2 to level 1. This emission is stimulated emission. So, it means that in order to use this 4-level system, I need a pump which will have higher frequency, higher H nu 1, this is pump, and another beam which will induce the stimulated emission having lower frequency. The energy gap is low. So, there are two beams I need in order to activate or in order to use this 4-level system. And this N1 state is very short lived, and that is why the population in N1 state rapidly decays to 0 state. So, under this condition, one can approximately write down that N1 is almost 0. No population is sustained in N1 state, and delta N, which is defined by N1 minus N2, population difference between 1 and 2 states, can be expressed as negative N2 because N1 is approximated as 0. N is the total population, that is why we can write down that population in the 0 state is going to be total population minus N2. N2 population is staying here. We have to write down the rate equations. The first rate equation is how the population doing in the N2 state, which will depend on how we are pumping, that is B I N naught, and how the spontaneous emission going on from N2 state. This is negative sign because spontaneous emission, this part will decrease the population and this part will increase the population, and that is why it is positive. Finally, we can plug this expression in these equations. On the other hand, change of population of N1 remains 0. That we have assumed that N1 state is very short lived, that is why no population is sustained there, and at steady state these two rates should be equal. That is a simple kinetic theory, and after doing little bit of basic mathematics we get an expression for delta n. Look at this expression, n is positive, total number of molecules, B and A are Einstein coefficients, which is also positive, intensity is also positive, everything is positive, that is why delta n becomes negative. When delta n becomes negative, it means that I have achieved population inversion, which means that N2 population is going to be greater than N1 population, and that is the condition which is required for getting population inversion. So, we have already seen that to achieve population inversion we need a medium with 4 level system. Furthermore, we have also understood that we need to pump the active medium to achieve population inversion. So, I repeat this idea one more time. If I have a 4 level system, I have to excite and create a population in the upper state with pump. I need a pump beam. Then with a lower frequency I need another beam to stimulate this. So, pump will create the population inversion and another beam we need to stimulate the stimulated emission. It is quite clear from this figure of 4 level system that the pump beam does not induce stimulated emission. We can recheck this one, this is your 0, this is your 3, this is your 2, this is your 1, that is the way we have defined previously. We see that H nu 0 3 energy gap is different from H nu 1 2 gap. Here 0 3 gap corresponds to pump photon energy and 1 2 gap corresponds to photon energy which will stimulate medium's emission. With this understanding, we shall go back to the Lambert's-Beer's law, which states that intensity of the emitted beam grows, amplification achieved exponentially with the length of active medium. This suggests that longer the active material, higher the laser intensity. In order to fulfill this requirement, active medium is enclosed in an optical cavity like the one which is shown here. This cavity is composed of 2 mirrors, so that emitted beam is amplified each time it passes through the gain medium. So, I need a pump beam to create the population. So, pump will create the population and then will start stimulated emission at lower frequency, and that will go back and forth within this cavity, and in the end this output coupler will give me the laser output. Mirrors together make up the laser cavity or resonator, and maybe they can be flat mirror or curved one. The cavity is aligned so that light reflects back and forth again and again and passing along the same path every time. Part of the light passes through the partially transmissive output coupler. So, the reflectivity of this output coupler, this is a mirror, is less than 100%, and this forms the output laser beam which can be used for the experiment. In closed cavity, different standing wave patterns are formed inside the cavity, which exhibits nodes at both ends, like the one which is shown here, and that's characteristic of any cavity which is trying to trap electromagnetic wave. Considering two plane parallel mirrors, this figure illustrates different longitudinal modes of the cavity. A longitudinal mode of a laser cavity is a particular standing wave pattern formed by waves confined in the cavity. The longitudinal modes correspond to the wavelengths of different colors which are reinforced by the constructive interference after many reflections from the cavity's reflecting surfaces. The longitudinal modes correspond to the wavelengths of different colors which are reinforced by the constructive interference after many reflections from the cavity's reflecting surface. So, longitudinal modes are nothing but the frequency components. We have been saying that an ultrafast pulse having a number of frequency components, and what are the frequency components which are present in the cavity, which the cavity will allow to sustain? These frequency components are called longitudinal modes. If we compare these two figures, then we find that this particular wavelength or the frequency component can sustain in the cavity, but other frequency components like the one, this red one, then green one, blue one, this yellow one, all of them, they can't sustain in the cavity. Due to destructive interference, they will die. So, a longitudinal mode pattern has its nodes locally. A longitudinal mode pattern has its nodes located axially along the length of the cavity. The longest wavelength which can sustain in the planar parallel cavity of length L is lambda by 2 equals L. Next one is going to be 2 multiplied by lambda by 2 equals L. Next one 3 multiplied by lambda by 2, and so on. Thus, wavelengths which can sustain in the cavity can be expressed as lambda equals 2L by m or in other words, the frequencies which can sustain can be expressed as C m by 2L. For two consecutive modes, if we consider this mode and this mode, so this is a plot of the modes which can sustain in the cavity. We see that they are discrete wavelength components. There is no frequency which can sustain in this regime. There is no frequency which can sustain in this regime. For two consecutive modes where m equals 1, they differ by 1, delta nu is going to be C by 2L. This relationship states that laser is only allowed to work at certain discrete frequencies given by Cm by 2L. A frequency domain view of basic operation of a laser cavity is pictured schematically in this figure. The resonator loss is taken as frequency independent, while the gain is assumed to feature band pass spectral response, a Gaussian emission spectrum of the gain medium. Let us say I have a medium which shows this spectrum, which emits in this regime, and this medium is placed in a cavity. In that case, all the frequency components present in this emission from the source will not sustain, only the portion which will sustain here. These are the portions which will sustain. And it will sustain above the loss. The medium emission will be absorbed by the cavity as well. So everything which is staying above the loss will sustain, and these are the discrete frequency components which can be sustained in the cavity. And these frequency components which can sustain above loss is called longitudinal modes. Here we can remind ourselves that there is another mode we have discussed, that's called transverse electromagnetic mode. When we have a source, a laser beam propagating like this way, and we place a piece of paper. In the cross-sectional section, we have seen a spatial distribution of the intensity. That's called TEM mode, transverse electromagnetic mode, and this one is longitudinal modes. So longitudinal modes are the frequency components which can sustain in the cavity above the loss, and TEM mode is the spatial intensity distribution of the laser. An electromagnetic wave propagation can completely be described using Maxwell's equations, which give solution for propagating electromagnetic plane wave. And we have seen that so if we take a plane wave and if we Fourier transform it, we get a single frequency omega naught. On the other hand, the time evolution of a pulse, for an example a Gaussian pulse, if we Fourier transform it, then we get another Gaussian envelope in frequency domain having width delta omega, which suggests that frequency content of a pulse is larger than the unique frequency of a monochromatic plane wave. Therefore, in order to produce light pulses, including ultrafast pulse, it is necessary to use a broadband source which can produce this many frequency components. For an example, a Gaussian 10 femtosecond pulse at 800 nanometer center wavelength. In order to produce this 10 femtosecond pulse at 800 nanometer center wavelength, I need 92 nanometer bandwidth. Requirement of large bandwidth to synthesize ultrafast pulse is an important realization. But when we place a broadband source in cavity, the laser cavity will allow oscillation of discrete resonance frequencies given by the equation Q Previously Q was represented by M, so we can use the same thing M here also. And M is an integer, C is speed of light, and L is the optical path length, the cavity. And these are the called longitudinal modes. So we said that we need these longitudinal modes, and we need many such longitudinal modes. Let's say we have Avogadro numbers of longitudinal modes which could sustain in the cavity. This, however, does not mean that we have produced ultrafast pulse. So having all these modes, 10 to the power 23 number of modes, doesn't mean that we have already produced the ultrafast pulse. The phase relationship between the different modes decide whether we can synthesize ultrafast pulse or not, which means that let's say I have many such frequency components, and those frequency components has to be in phase. And if we cannot maintain a constant phase relationship among frequency components, then we'll have destructive interference like the one which is shown here, and in the end intensity of that system will fluctuate in time. That's why modes which can sustain, they should be in phase and then locked. This is an important requirement to produce ultrafast pulse. Having many frequency components is not the only necessary condition to get ultrafast pulse. First, we have to get many frequency components, and then all the modes should be locked. If phases are not locked, the instantaneous intensity will show fluctuations. On the other hand, if the modes are having constant phase difference, the laser is said to operate in mode lock regime. The purpose of locking the modes is to organize the competition between modes in such a way that the relative phases stay constant, which results in ultrafast pulse. In general, stimulated emission in a laser cavity creates coherent laser modes. However, due to different factors, modes do not stay in phase all the time. In order to create ultrafast pulse, we need to achieve mode locking. How do we achieve mode locking? The simple answer is to use saturable absorber. We'll stop here and we'll continue the subject in the next class.